Good afternoon, everyone, and welcome to the May 2026 edition of our designTimber webinar series. In a moment, we're going to be hearing from the expert team behind a fantastic piece of timber infrastructure, Rafter Walk. But just before I hand over to them, I'm going to say a little bit about Timber Development UK, so you know who we are. TD UK was formed in 2021 from the merger of TRADA and the TTF, the Timber Trade Federation, which makes us the largest supply chain body in the UK for the timber sector. We span designers, architects, engineers, through to the importers, the sawmills. So we cover everyone who works with timber in the UK pretty much. Here you can see our three mission statements. We seek to connect the supply chain, to lead best practice, and to accelerate a low carbon future. Because as many of you know, timber is one of the most sustainable materials that you can be building with. Now we seek to achieve these three missions in a number of ways. One being webinars like the one you're watching. Another being the many other outputs that we have. You can see a couple of them there. There's Designing Timber. We have two flagship magazines that are printed. One is Designing Timber and one is Supplying Timber. They're packed full of innovative timber projects like the one that's the subject of this webinar. They're packed full of CPD and all the latest news about the timber sector and timber as a building material. You can also see a couple of examples of the documents you'll find in our knowledge library. Our knowledge library is crammed full of timber knowledge sheets, such as the one you can see there on using SIPs, structural insulated panels. If you're interested in a particular timber methodology, you will find a timber knowledge sheet lurking in our library that will tell you all about it. It's a fantastic resource, and I suggest you make the most of it. Another of our really good documents there, moisture management during construction. As many of you will know, moisture is an essential topic that you really need to understand if you're building with timber, how timber and moisture relate, all the things that are best practice when you're working on a timber project. And also you can see one of our case studies there. That's the Hive, a great demountable timber building. But you'll find plenty of other case studies on our website that can show you practical examples of the kinds of things you can build with timber and the challenges and opportunities that those buildings provide. Do make the most of our knowledge library. As well as our designTimber webinar series, we have a new webinar series that will be starting up shortly afterwards. Over the summer, Timber in Construction 101. It will be very technically focused, so it will be really diving into some of the key technical subjects and topics that accompany timber design and construction. Another great free webinar series that we're putting on. And it's really thanks to all of our members that we're able to do things like that. As I just showed you, we have an awful lot of great resources on them and on our site, and many of them are free for everyone to access, not just members, but we also do have a lot of detailed technical information and other resources that are member only. So we do encourage you to join if you're not already a member. We can't do it without you. So please consider membership if you're not a member. In a couple of seconds, I'm going to hand over to the representatives of Whitby Wood and Xylotek, who are going to be presenting a very informative webinar for you today. Just a couple of bits of housekeeping. I would urge you all to make use of the Q&A button. You can find that at the bottom of the screen. Please do ask any and all questions that occur to you. Stick them in the Q&A box and there'll be time to answer them at the end of the webinar. So now I'm going to stop sharing and start the webinar proper.
Thanks, Matt. I'll take over from here. Hi, everyone, and thanks to those of you able to join today. My name is Gioele Nunziatini. I'm Associate Director Structural Engineer at Whitby Wood. I've been here for almost 8 years. And I'll be here talking, as Matt said, talking to you today about this amazing project, Rafter Walk, that I was involved since its early concept stage all the way through to completion on site. The part of the presentation I'll be covering will set the scene a little bit for where we are, the site, the history of it. You'll see why it's relevant when we move on to the design intent and the design development, ultimately concluding with a review of and a summary of the design solution. We'll, being myself a structural engineer, we'll have like obviously a structural angle to it. So we'll review that solution and ultimately talk also about overall construction sequence of building something like this in central London before then handing it over to Martin. So starting with a bit of project introduction, setting the scene for where we are. So we are in rather high Surrey Quays, and historically this dockland area has been developing in, starting from the first dock built in the early 1700s, all the way to Canada Water, for example. Canada Dock later redubbed Canada Water, built in 1876, and it was a series of docks connected by waterways, further linked to the River Thames, where ships would come in, unload their freight, and that would be further on processed. You can see on the left a picture of the deal porters, the specific workers on Canada Water, offloading rafters and floating them onto the water, onto the dock itself, to the warehouses built on the shores. This area has then seen later redevelopment as with the mechanization of the process, the need for these large docks shifted away from such a central area and shifted to a less labor-intensive set of operations. This area, being so close to central London, was redeveloped in the 70s and 80s to a large master plan with a mixture of new housing provided, a bit of commercial space, as well as some green space linking them together. Some hints to the history of the previous scope of the dockland can still be found, have been retained and integrated as part of this redevelopment, such as Stave Hill in the middle of the green space. Which was actually an artificial hill built with material rising from just reshaping and filling of the docks, as well as Surrey Lock, which is this lock you can see here in the top central picture, which is actually a Grade 2 listed building. So after this redevelopment in the 1780s, there's a more recent master planning redevelopment to converting and repurposing predominantly the commercial area of the 70s development master plan into more of a central new neighborhood, taking advantage of the proximity to central London. This has been pursued by the developer British Land in a joint venture with Australian Super to redevelop the area that you see hatched in red between what's left of Canada Water and Greenland Dock in this area. So this whole predominantly commercial area being redeveloped. So the last bit of project introduction of setting the scene basically focuses on Canada Water as a key part of this master plan, this multi-year master plan, part of which was exactly Rafter Walk. So this phase focused on the redevelopment of the dock as a whole, with a construction cost roughly split between 50% on landscaping and redevelopment and refurbishing of the site of importance for natural conservation. So basically the landscape and the marshes around it, as well as this new link structure, this new boardwalk that is referred to as Rafter Walk today. So linking that history, heritage of the site to what is the design intent couldn't be done without an artist statement by Asif Khan, artist and architect behind the conception of this structure. And I've put the entire statement in here. This presentation is being recorded, someone can go back and read it in more detail. But the key passages here that really express how that heritage has been then fused with the proposal of and the designing that has been ultimately built is the two highlighted in yellow, which I'm going to read for everyone. So at Canada Water, I've been working with form, color, and rhythm as abstractions of motions and memory from the history of this dock, its timber cargoes, and forests and rivers of Canada from when the timber originated. And Asif continues by saying, the bridge is a chronograph, a drawing that records time, capturing the emotions of these individuals. It's easily forgotten that forests on the other side of the ocean helped build London. Many layers of that story are embedded here. I want to invite reflection, wonder, and contemplation of the past as Londoners walk in the footsteps of their forebears across time and upon water. So you can see how the history, the heritage of the site has been a key element in the mix, producing this design intent here. So here's just a quick defining aspects of that is design intent. Obviously the shaping plan, as well as that undulated elevation profile, are key hints of that heritage being basically translated into form and baked into this structure. Obviously, there were a series of parameters that were explored through the design studies carried out in developing this concept. We spoke about the plan alignment, the vertical undulations as well, but every other aspect was explored for this. The design constraints from the site were limited in terms of clearance required underneath the bridge. That allowed basically the design to develop and stretch in a very different way to ultimately converge on what was this solution and this proposal that's then been built. So the pier design, the number of piers was explored. The materiality was a big one, as I'll cover briefly, and then Martin will cover in more detail regarding timber specifically. But there was great level of studies done on the primary structure, the decking, the parapet, and the architectural fins. Ultimately, the architectural finish, which is the first aspect of the project that the end user will experience, was also explored, but that was done again in association with the materials and the overall combination of these parameters. So these design studies and this design intent culminated into a design solution, which we'll give you here as a summary, and then we will go into more detail into each one of these structural categories. This is first and foremost perceived as a timber structure. There was a great use of timber, and every single timber element except the architectural fin in light blue have a double architectural and structural function. But at its core, this is a steel structure. So the substructure and the primary superstructure are steel structures, which we'll see and understand why in a second. Obviously, there was, in exploring the materiality, there was a great deal of consideration done on taken onto in terms of like durability, maintenance, sustainability, and so on. So all of these came together and converged into this design solution and this arrangement of different materials. The timber comes into its own when we then look at how the balustrade assembly support and how that, together with the timber bearers in blue, supported the timber deck cassettes. And then ultimately these support, as I said at the beginning, the only non-structural element of this typical cross sections, which are those timber fins, a hint at that heritage of the rafters being floated onto the dock. So I'm going to now dive into each one of these aspects a bit more to give you an overview of why they were designed as such. Starting with the substructure, what I like to always say is that no matter what the structure is, ultimately will always be founded onto the ground, such as this one. So we had to deal and mitigate the unknowns in working within an existing dock, an historical dock that in the past 170 years or so has been infilled, reshaped, and ultimately, created this layer within the dock bed of made ground with obstructions, with a risk for UXOs. This area was heavily bombed during World War II. So there was this element of that layer of made ground that we needed to digest and understand whether it was suitable or not. So here's a more diagrammatic representation of the typical soil profile, ground profile, and the proposed substructure. It was soon, due to the level of uncertainty, it was soon basically determined that made ground was not fully suitable for structural application, certainly for ultimate stability. Therefore, the structurally relevant profile is more in the middle, whereby we have a layer of about 10 meters of unsuitable water and dock bed before we get to structurally competent strata, such as clay, where our foundations can transfer vertical and lateral loads. So our static scheme was more akin to the diagram on the right, where we had 10 meters before any lateral or vertical loads could actually be shed into the ground by the foundation system. This means that although the Rafter Walk itself, the superstructure is quite shallow to the water and to the landscape islands, from a structural point of view, it behaves more like a tree top walk, 10 meter in the air. So that is a key consideration that we needed to keep in mind in terms of its lateral performance and behavior against dynamic loads and thermal loads. As a summary, this is the substructure solution, therefore. So the predominant solution for the Rafter Walk and its link bridge was pairs of CHS driven piles. Quite a positive story in the fact that we were able to reuse an existing stock of steel tubes and repurpose them as steel-driven piles. There's a bit of a sustainability win in there. And then when we come to the ends of the north and south abutment, we needed more laterally competent restraints for keeping the overall stability of the structure in check against its desired performance. So we have a ground-bearing raft solution at the south abutment onto ground stabilized and ground improved dock bed, as well as CFA piles at the north, closely spaced. The change was driven from steel-driven pile to use CFA pile was partially driven also by the proximity to the underground network rail asset in the form of the masonry tunnel for the overground line that goes through here. Moving away from the ground and into the superstructure, the main bridge forming the key central portion of Rafter Walk has a simple ladder-like planned structure with the arrangement of two primary longitudinal CHSs coupled by primary cross elements highlighted in yellow. These primary cross elements had the function to take the loads back and connect them to the piles that you can see as represented as a pair of circles either end of this plan view, but also to couple unbalanced live loads between one side and the other of this boardwalk. The width of the boardwalk is 4.2 meters, so it could have some unbalanced live load pattern from one side to the other that would generate torsion in this ladder, and that was taken out by pairing the elements and coupling them with cross elements. Secondary cross elements and cantilever stubs have also structural function, but it's more related to supporting of the balustrade assembly as well as the decking solution, which I'm sure Martin will cover in more detail in terms of sensitivity done there. The key considerations here that is clearly visible in plan is how the primary longitudinal CHSs is slightly recessed from the tip of those green cantilever stubs, as well as how the piles are then further recessed in rather than placed underneath the primary CHSs. So these were coordinated with the architects through design development to hide away that as much as possible the steel elements, so that that perception of a timber bridge could be elevated. At the same time, it has a double function of sort of like creating a more clean, streamlined lines that draw the attention of the eyes. Similar solution was adopted for similar narrative and design philosophy was adopted for the link bridge. So the link bridge provides access to the middle of the main bridge of Rafter Walk, at the same time works as a key lateral restraint for that lateral behavior we spoke about just a minute ago. Due to the simpler geometry, there was no requirement to use CHSs. This was straight in plan and with a sloping elevation, but without any undulation. So it was easier to use open sections and streamlined fabrication. Moving to the ends of the main boardwalk, we find the abutments. As I said before, these needed to be able to take lateral load independently without being connected to the existing dock walls, due to uncertainty to do with the capacity of the historical portion of the dock wall. So this took the form of like steel structures, again, clad in timber, using the same principle, extrapolating the same principles for the balustrades and the decking as the main boardwalk, but essentially with more of a lateral capacity in the form of a U-shaped shear wall at the south and introduction of some vertical bracing in the north. Moving on to the details, obviously, I'm just going to touch base upon this. Martin will go into more of an in-depth review. There was during stage 4.5 and stage 4, and as well as throughout stage 5, there was a great level of conversation with Xylotek as main timber contractor, as well as the main steel fabricator, in terms of understanding the interfaces, understanding the fabrication challenges from one material to the other, site tolerances, and as well as trying to optimize as much as possible the level of details. So digesting what is a undulating S-shaped type of geometry with ever-changing angles between the steel and timber elements, and trying to streamline it into a type of detail that offered the maximum repeatability. So there was typical details, there was bespoke details. We had to think about how to marry different materials. We had to think about how to marry the superstructure to steel-driven piles and take out those tolerances. But I'm sure Martin will go into more detail about this, the intricacies of these aspects of the design. As last part of this of the presentation, I just want to give you an overview to the construction process as a whole. And I put this picture in here. This was taken from, it's a snippet taken from a drone shot during construction. And you can see left to right, basically a chronological progression of how this main portion of the Rafter Walk was built. Obviously, starting with substructure and foundations, which were largely aided by the construction of a temporary causeway. So you can see the area that nowadays is open to water, has islands, has channels with water, was temporarily infilled with a causeway, so that essentially most of the construction could happen on land using standard equipment rather than having to work from barges. The approach was sequenced with multiple materials and multiple contractors having to coordinate and work seamlessly on site. Substructure would go on first, then the steel would be erected, and then the timber would follow in a sort of like staged approach. Key item was the link bridge, so that connecting point to the middle of the bridge that we just mentioned had to be delayed so that the use of this causeway and access to the north portion of site past the link bridge wasn't restricted. So that meant that everything that needed to happen to the north portion of site was to be concluded, including landscaping, including finishing, and anything requiring heavy lifting. So a couple of pictures during construction phase. Obviously starting with the foundations, those are steel-driven piles, as you can see, erected, installed on dry land, thanks to that causeway, and the large capping plates that needed to be oversized to cater for any tolerance requirements. Steel was entirely fabricated off-site, delivered to site in the largest section possible, and then these were erected onto those plates and bolted together so that steel construction on site could happen quite quickly. And then timber started coming on, and again, Martin will cover this, but as much as possible favoring off-site fabrication in terms of creating modules, cassettes that could be brought to site and with minimum site intervention, with the minimum amount of site intervention just adapted for tolerances and geometry to suit. So the balustrade would come on, then the bearers supporting the decking cassettes would be installed with some elements of site adjustment and site drilling, and then ultimately the cassette would make it to site and deck out the entire boardwalk. And last but not least, obviously, finishing touches. So we spoke about the architectural fins that project from the underside. Those were some of the last pieces to be installed, same as the site finished handrail, and obviously touching up of paint as and when required. So that brings us to completion. A couple of nice pictures here for those that haven't been there in person or haven't had the chance to go yet. These were some nice pictures taken just after its inauguration, and you can see from the last bottom picture how carefully hidden away and designed the lighting was, so that it's not visible during the day, but through its dimmable features can be used to enhance the form of the structure and its appearance at nighttime. That brings my part of the presentation to a close. I'm just going to stop share and pass it on to Martin.
Great, thanks, Joel. Fantastic introduction and handover. So yeah, I'll talk a bit more specifically about the timber elements and sort of the process of their detailing, fabrication and delivery on site. Just to introduce myself, so I'm Martin Self, I'm a design director of Xylotek. We are specialist subcontractors doing timber structures and also consultants, so we get involved in projects early and help steer them into realization. We specialize in non-standard structures, so quite a diverse portfolio, non-standard in different ways, whether it's complex site condition or complex geometry, but yeah, looking to sort of enable timber projects where there's a challenge to solve. So just to give a bit more detail on the team that we worked with. So Galdris, main contractor, sort of full kind of landscape contractor on the dock redevelopment, and the boardwalk fell within their remit, so we were their subcontractor. I think Whitby Wood joined us as a subconsultant within sort of our design responsibility, so we had a nice tight working relationship with Joel and his team. Just to list some of the suppliers there, machine the key ones. Lots of people contributed, lots of companies, but the main ones. So Vandenberg, the Dutch.
Martin, can you hear me? Should you be sharing a screen at the moment?
Yes.
We can't actually see it live.
I thought I'd got to that point. Sorry. Thank you very much. You haven't missed too much. Let me just, just to pick up. yeah, that was the Xylotek introduction page, just a sense of our portfolio there and the sort of mix of projects. Here I was just listing um, the team with us. So I was mentioning Vandenberg, who hardwood suppliers, Dutch company, the Accoya, so the material of the fins came through SBM Fastwood. The key bits of machining was done by Oakwrights in England, so worked very closely with them on the sort of DFMA process, the steel by SH structures. So I'm going to talk, I suppose, focusing on some specifics about how we turn this thing into reality, how we took the engineering and the architectural principles, very sort of clearly conceptualized, but not yet ready for actual manufacture and actual realization. So how we go through those stages of taking that sort of stage three, level intent into something that's realized. Maybe just to sort of recap some of the principles behind this. So, steel substructure, but the visible and the kind of contact material is all in timber. That's the prime sort of element of the expressed structure. It's 120-year life. The durability is really key, and then a key element of the modularity and the ability to pre-assemble to bring elements efficiently to site and do a very efficient construction assembly on site. There's this clear hierarchy between the elements of steel, the substructure, the balustrade, the deck, and the architectural fins. I think maybe to sort of mention there's a real kind of tactility and kind of a solidity. If you feel this structure, it's has this fluidity, but also a very sort of good sense of sort of the density of the wood. You can touch it, you can really get a good sort of interaction with the materiality. Connections are concealed where possible, so it's hard to spot the nuts and bolts and screws that are holding it together. There's a blind side or hidden fixing as much as we can. And then the key thing, which we'll talk about quite a bit, is the geometric complexity. So you can see in this image, it's sinuous in plan, it curves backwards and forwards, and also vertically. So it has this rise up and down within it as well, which really adds to the sort of fluidity of it. Obviously adds complexity in its manufacture dealing with that double curvature. We'll talk about that. Prime consideration is the DFMA, the efficiency of digital design going straight to manufacture, straight to the machine, the directness of that, and then the ability of really controlling tolerance, production, and getting things cleanly to site in a way that we know is going to fit together. And just to mention there, I don't think we cover it again. So the bottom point there is obviously this very strong red stain, really key to the architectural presence of the project in the site there, and then the grey coating on the Accoya fins there. That's sort of the principles. So I'll talk a little bit about the timber supply and the kind of procurement. I'll go into specific elements. We'll talk about the balustrade. We'll talk about the deck, how we delivered those, how they developed, and then how everything came together. So yeah, it's a major bit of London infrastructure. I think actually the first sort of long span water crossing since the Millennium Bridge. It's a key sort of landmark feature. So yeah, long design life, durability absolutely essential. Right from the outset, driven by the need for durable hardwoods to be deployed in this, and for it to be done through a full FSC, absolute clarity on the chain of custody and the sustainability of the sourcing of that wood. So various stages gone through there, different options, commercial considerations. I think the Eki that was in that original considerations that evolved into the Kumu and the Red Angelum that I talked about here, Brazilian supply. Just to mention as well, those sculptural fins that sit to the side, which I kind of see there's a question already about that. Yeah, they are purely sculptural elements, capturing the sort of the flow of the form. They're made of Accoya, so that's that acetylized pine material that's then glue laminated in this case into those curved pieces that stick out the side. Maintenance considerations obviously key, and then just fundamentally the supply chain consideration being really important. Just a bit of the data on those species is either dense, tropical hardwoods. I think in the P family, kind of interestingly, grew up to kind of meter diameter. both highly durable, class one, both in that high strength D50, D60 category. The red angelin more kind of consistently red. The Kumru sort of actually varies a bit between the yellow and a redder color, both around the density of water, so you don't want to sort of drop it in a lake. It would sink potentially. Hard to work with, particularly the Kumru, tough on the machines. You have to pre-drill everything. You really have to think about the manufacture because it's very different to even an oak, a UK hardwood, very different to work with, and obviously very different, very, very different to a softwood. Interesting, the red angelim has a rancid smell. There's an acidic kind of chemical within it that gets released as you're working with it. So as I was mentioning, the chain of custody and the confidence and the sustainability was really key. So Vandenberg's they're the leading European FSC-led international hardwood supplier. So we sourced through them, which gave very strong confidence to the client and the wider team that we were sourcing responsibility. And British Land actually commissioned independent assessments to kind of audit that supply chain as well. So they went right back, the data and plot from which the trees were sourced. And this company Canop did a retrospective analysis of satellite imagery of those plots to track sort of year on year the change in the canopy cover as a measure of the sustainability of the forestry there. So confidence that only a small percentage of trees are being felled, that it was being done in a sustainable way that was preserving the full ecology of the woodland. Okay, so I'm going to talk about a couple of elements in particular which sort of illustrate the process and the thinking. So the balustrade design, it's sort of think in a way quite a simple thing. It's it's some sort of vertical spindles or the handrail and some way of fixing it to the main bridge deck, but the complexity that comes from that curvature sort of brought some interesting considerations and how we kind of reconciled the fabrication, the pre-assembly, the assembly with that geometry is the story I'll tell in the next few slides. The left image, you can see the radial setting out. So there's an 80 meter and a 90 meter radius. I think the top segment in the image is the 80, and then it goes to the 90 in the other part. So there is a sort of rationality to the curvature in plan, but there's also the curvature in elevation. So you see it's fairly subtle, but goes up and down probably, I don't know, 400 mil or something. Actually has three low points. So it sort of starts high and then goes up and down across the span of the bridge. You can see it in the upper left image in that one. So it basically means there's no sort of commonality really in the balustrade elements. So we went down the route of sort of accepting that every part of the balustrade would be geometrically different, and kind of worked with that, and then worked through a logic of a assembly that allowed that to happen easily. This captures some of the design evolutions. This is sort of the stage 3 solution. So you can sort of see top right how things sit on top of the steel structure. There's these ladder beams along the edge, and very sort of kind of anonymously, you maybe can't see it there, but there's a sort of label saying curved timber edge bearer, 250 by 150, which sounds fine, but in practice that's a tricky and expensive thing to do with that double curvature. So there's a lot of work then done to sort of think through how to evolve that into something a little bit more cost effective and sort of easier to realize. There's a few moves. There's breaking down the balustrade panel lengths into shorter pieces. You can kind of see here. So you could then use a shorter faceted element. Just getting clear about the principles of that. So having an edge member that was straight and varied with the sort of elevation angle, the up and down, but the spindles all kept truly vertical. So they always pointed in the sort of true Z dimension. So they were kept consistent. They weren't sort of changing angle with the curve of the bridge. Lots of studies done about the relationship of the steel and the wood, and the possibility of the ladder and exactly what did what. The need to pick up the fins as well onto something good and solid. So things ultimately came to, well, I think Joel showed this earlier, but a sort of simplification in a way of having a steel stub as part of the steel structure welded to the CHS, picking up a single edge beam in straight facets, and also the same element picking up the fin. So spacing them at the fin dimension, just bringing everything together, making the panel smaller, easier to handle. I think just about two people could kind of manhandle them into position, and then just bolted back, sort of hidden bolts back into the steel there that you can see, and then those infill pieces coming in at the end and kind of cross-screwed in a hidden way, so everything was tied up. You can probably pick that out in the maybe in the right-hand image there. Some of the spindles had holes drilled all the way through them vertically to pick up the cabling for the lighting. Quite a lot of sort of specific detail within there. The right image now shows just the screw fixing of the spindles. Looks simple, but I think quite a lot of work for Whitby Wood to get this refined, getting the edge distances justified, getting a kind of optimized relationship between the spindle dimension, the spacing of those, how everything tied together. So, like Joel was saying earlier, a lot of very close interaction between us kind of through stage 4 with the sort of design, anticipating fabrication hat on, and the engineering and the architectural working together. So everything was synthesized really well. So this is then the sort of story about how these things were actually worked out. So let's talk through this a little bit. But on the left-hand side, you can see the simple jig in which the pieces were pre-assembled. So you can see there the edge beam piece in the red angelum, the Kumru spindles poking up, how they're kind of held in this jig that allow the geometries to be set. So the edge piece, the bit that's sort of bottom left nearest us with all those screws holes, that was fabricated by Oakrights on their Humdinger machine. So, CNC machine, not normally used by them for oak framing, but yeah, used for the cutting of these elements, for drilling all the holes, all the counterballs, all done digitally. Each one of those different all the way across the bridge. I think 500 or so different pieces, adjusting for the angles as it flows along. So a very careful definition of those digitally, fully three-dimensionally defined by us, and then fed into their workflow. We actually, because we had the digital information ready to go and held in CAD work, the software that's sort of specialized for timber construction, we're able to go straight into. We're actually able to export the machine file, the BVN file that drives the Humdinger, saving a lot of time at the fabricator, at the machinist side. They could just take files in a good, controlled, organized way. We could sort of sequence them in the order we needed them, straight into the machine fabrication. And you can see there, that's the pre-assembly that happened. So this is stuff that's within our model and thinking of this. So I guess the different colors top right are showing all the different conditions that we have along the bridge, the different radiuses, the specials that we have around the abutments and the bit that joins the link bridge. There's some bits where the spindles drop lower, and there's a sort of slot for kids to look out of at the view, something like that. So there's quite a lot of sort of special conditions alongside the ones that are more consistent. And as I was saying, like we're modeling every screw hole because they're pre-drilled, every counterbore, every single screw in the whole bridge is modeled in the CAD work model. Tens of thousands of components to get an absolute definition of everything, and then control of all of that. So naming of every piece, the sequence order, the specifics of all of that, how things will come, the simulation of the actual machining being done. So the Humdinger machine doing its operations virtually to give confidence that the reality could be made, that you can get the tool paths to work, that things don't clash. That was a special piece, that the one that sort of showed there top right, one of the corner bits where there's some extra machining cuts on there to get around a curve. So anything else to say on this? I mean, you get the idea probably. It's just a process of going from the global sort of setting out geometry, the reference geometry logic that's defining those radiuses and curves in elevation, all the way through, down to the sort of center line, the positioning, the setting out points, the structural kind of center line geometry that Joel will be working with, through to the full volumetric definition of all of these features on every piece of wood, and obviously maximizing the automation of that where we can. Quite a lot of work done in Grasshopper and Rhino alongside the CAD work. That's a machine in the background and the sort of information we're giving. So we're asking them and really planning out day by day exactly which bits they're going to be doing, because we're then needing to feed it in I think Joel's image, which showed the flow of the bridge, like the construction going from one end to the other, that was the reality, so we had to kind of work and sequence things carefully in an order that matched the assembly. Then the jig, which we showed a picture of before, in itself quite simple, which was in a way part of its beauty. The actual jig is just this rectangular frame you see bottom left. That consistency of the spindles always being equally spaced and vertical, so that's sort of set. You drop them in, kind of set the cuts top and bottom, and then what varies in the jig is the position of the edge beam member, so the pink piece in this. And very simply, so rather than doing a drawing of every piece, there's just a spreadsheet with the key dimensions, labeled D and C and B in here, so the dimensions that would set the corners of the edge member within this frame. So there's obviously a series of these things made, and then the data for that driven out of a Grasshopper script. So one of our team, Marina, worked very closely. So yeah, Marina and Nate, amazing designers, just spent a lot of time thinking through how to get all of this sort of rigorously worked out and a workflow established that would give the data for this process. As it's a lot of it done in the Grasshopper kind of Rhino world, outputting that numbers. I think just runs as a video. You might just about get a sense. You maybe see where my mouse is pointing that the edge beam is sort of moving around as it's kind of working its way along the bridge, and those dimensions being adjusted in each position. So basically those millimeter dimensions are what are given to the team on the workshop, and then they set those against the tape measures on here, all pretty simple, fairly robust, easy to check. There's a set of check dimensions as well as the set out dimensions. So these blocks, which have come from oak rights, dropped in, positioned to the data, and then the screws put in. And that's it really. That done 500 times, producing these pieces. You can see here this bit of steel becomes the top plate, so that gets screwed onto the top. There's a sort of line that runs through the top of the spindles over that, and the handrail piece gets fixed up through that steel plate into there. I think if there's anything else to say about that, but sort of see the thinking behind it, how to take the complexity of the geometry variation into something that actually in reality on the workshop floor could be simple enough to be able to do consistently and efficiently. There they are, the sort of families of them going out of the workshop, sequentially going out, craned in, moved around. You can see the fixings that I showed earlier there coming into place. So yeah, the balustrade, maybe just to mention the handrail. This is actually the mock-up, so a sort of softwood mock-up of the detailing there. So quite a bit of complexity in these. This is one of the more tightly curved bits. So in the end, they're done in the hardwood, the stuff you can see in the top of the middle image, in the Kumru as well. You can see some of the details on the left-hand side there. So sort of male-female plug to get everything to come tightly together. Sort of socketing to bring everything to fit, and these tension fixings to tie everything together. So everything came together very nice and tight on the handrail elements. And I guess that leads us then into talking a bit about the deck. So the other sort of prime element. Another set of challenges here. So again, dealing with the curvatures, that curvature in plan in particular. Absolutely key architectural sort of move was to run the deck boards longitudinally along the flow of the bridge. I think if you think about most bridges, you'd probably run the boards laterally. It's obviously easier to kind of run them just a sort of perpendicular lateral path across. Running longitudinally and curving them presented some good challenges, and we'll talk through that for the next minute or two. So that sort of flow and testing experience being really key. Lots of R&D, lots of back and forward, lots of workshop testing, prototyping, and then back and forward with Joel's team, really like trying to understand how we best do it. Again, lots of variation, bit less this time because we were able to kind of run with the radial geometry. So there's the 18, 90 meter radiuses, the sets of panels, different lengths kind of worked out in a way that the joins would always miss each other by, I think, 250 mil as a kind of minimum. So long, short, medium sort of lengths of the panels. So self-similar along the oranges and yellows, and then different on the other set. So 6 kind of standard ones, the straight ones on a link bridge, and then a bunch of specials at the ends in the abutments. And then the grey bit's actually done more sort of in situ. So those are patches also of decking done at the abutment ends. Lots of early stage testing. So yes, I guess the idea was to be able to curve those deck boards, and lots of different options are thought about that. These are versions with a sort of all timber deck and locking in curvature with kind of truss arrangement in the wood. This is sort of testing the more extreme end of the curvature. The steam box in the back, so we tested steam bending, which is actually quite sort of inconsistent and I guess laborious, and yeah, probably too time consuming for this. So the ambition was to be able to cold bend these, just elastically bend the pieces in the pre-assembly. Another option would have been to subtractively machine the geometry out, to take the profile out, because of the complexity of this profile, that has recesses for the fixing, a relief cut, another cut for the anti-slip strip to fit, to machine cut that in a curved shape. They're very sort of complex in itself, and also wasteful because you'd be cutting a curve out of a wider straight plank, and this wood's very precious, so don't want to do that. So yeah, so the process developed to just go back to that truss idea, but to do it with steel cables. So below the deck, there's a couple of steel sort of edge members, kind of cord members in the truss sense, and then the tension cables, so where they need to be to lock the curvature in. So you could bend one of those boards by hand, but when you have 17 of them laid up, they cumulatively add up their spring back. So you really need to lock in that geometry really carefully. So these are pre-assembled panels, done in the workshop, and then carried to site and dropped in one by one. These are the Whitby Wood comments on our drawings, just to show you the amount of backwards and forwards and sort of refinement having to go on in thinking about this. And here we are. This is now the reality in the Xylotek workshop. So CNC jigs for each of those different conditions I was mentioning, setting the positions of the cord members, the secondary bearers, and then paths where the steel cables come in. You can get a sense of the curvature that's been locked in. The staining happens at that stage as well. Another view of the jig there with the cables coming in and the turnbuckles and the tightening that gives a little bit of adjustment if needed to get the collective curvature locked in. There's a panel coming in, so very nice, totally pre-assembled, locked in. No need to deal with those springback forces on site. They're now self-contained panels and able to be flown in on site. I'm just going to rattle through some site pictures. You've already seen some. The steel and the primary bearers coming in, starting to move along there again from one end to the other. Now the balustrade pieces coming in, like we were talking about. Yeah, more progress. Looking from the other end, deck panels starting to arrive on the right-hand side there. Some need to sort of shuffle and line up, but generally things working really, really nicely because of the care taken in the workshop to get everything in the right position. The coil fins coming in. Mentioning those abutment areas where there's sort of larger areas of decking, so and some nice transition from the deck flow into just parallel planked zones. Having to navigate the tight curvatures at some of those abutment and connection zones. So a bit of sort of hand crafting, I suppose, on site to deal with those ones. But you get a feel for it there, just how the bridge nicely flows into that end zone. Yeah, that's pretty much it. A couple more images. We're probably slightly over time. Apologies. I guess, Joel, I think you were maybe going to jump back to just another little sort of anecdote. So there's another sort of separate bit of structure that Xylotek didn't deliver, called the dipping pond, which has its own interesting story just around some timber piles that Joel knows the story of better than me. So I'll hand over to him at that point.
You can be very quick, Joel. Yes.
Yeah, will do. Thanks, Martin. Back onto this presentation then. As Martin said, there's a secondary structure away from the main boardwalk, away from Rafter Walk, called Dipping Pond, later redubbed Discovery Pond, which had, again, adopted as much as possible of the same principles, so that ladder structure, superstructure, and so on. But due to the smaller scale and the lighter loads, smaller balustrades, no fins, we were able to actually use timber as a material for the piles, for some of the substructure supporting this. And again, we use the similar ladder superstructure supported on pairs of timber piles. But these timber piles basically created some side challenges as well, because when it came the time to drive them into the ground, unfortunately they hit some obstructions that meant that the tolerances were greater than previously considered in the design. Further to that, the size that was required for driving them into the ground was larger than the size specified in our design for connection to the superstructure. So they needed to be finished on site and sculpted back to the correct diameter that was required for the design. So that was done. Those two items were considered in combination. That meant that the resizing of the head of the piles was done in an eccentric way to the rings of hardwood and softwood. So what we ended up with is, you can see in the top three pictures, we had like eccentric head piles to the main body of the pile. And because it was peak summer and this wood was still, losing some moisture, and this hard green hard, you can see how I split with a term that with a behavior that resembles almost like the layers of an onion peeling off. So we needed to, obviously we wanted to use these piles, we wanted to make good use of them. They were in the ground, were procured and installed already. So we ended up working closely with revitalised, for example, and specifying a strengthening solution that enabled us to use these piles to support the secondary structure. So those piles were reinforced with cross screws, and then ultimately all of the cracks were injected and stabilized with one type of resin to ensure that the durability of that wasn't compromised. And then was the bespoke capping element that we had to design to consider the eccentricity was lowered in place. Another resin was injected to make sure there wouldn't be any gaps left for water and air to get into between the steel capping element and the timber. So another opportunity on this project to use timber as a material. And conscious of time, I will jump into the last slide.
Thanks
Thank you
so
very
much.
everyone.
Two very, very informative presentations there. So we're going to try and race through some questions. We might overrun slightly. I'm just going to start by noting that a couple of people had asked about the concealed fixings, and I'm just going to, for purposes of time, just mention that Gioele, you pointed out that most of the fixings are visible from the underside of the structure because people had asked about inspectability. And you'd also pointed out that truly concealed ones were generally not crucial for the primary load path. But yeah, I thought it was interesting how well you had done that the fixings to the sort of at first glance would be completely invisible, but from an inspectability point of view can be accessed from underneath. I don't know if there's anything else you'd like to say about that point.
No, I think between Martin and myself, we've shown this detail on the left that you can see here. So these concealed infills that you can see with a sloping top wedge finish on it. Basically, they were used and are, correct me if I'm wrong, Martin, but fixed from the back to conceal the primary fixing. So you can inspect the primary fixings or remove some of these concealing elements to quickly inspect the primary fixings from the outside. Everything else should be generally visible either from the top, because the fixing of the decking are just recessed in between the decking. You don't see them, but they're just visible if you focus on them, or from the underside predominantly.
You also typed a very good reply to somebody asking about structural design life and durability considerations. I was going to ask about that too. In terms of corrosion and that kind of thing, and with exposure to the elements, obviously moisture, both with the steelwork, the connections, and the timber. I'm just wondering if either of you would like to say a bit more about that.
Take that, Martin, if you want. So from a steel perspective, the substructure steel is designed for corrosion rate and reduction in thickness arising from that. The steel superstructure has been galvanized taking into consideration the 1 micron per year corrosion rate specified by the Galvanized Association. And the specification exceeded the requirement, and ultimately the thickness that we're able to achieve further exceeded that. So there's extra protection in there. Timber-wise, and Martin, feel free to jump in. There was a lot of research and liaison done with Rotherblast as well that provided most of the fixings from memory in terms of using the appropriate screws, considering the acidity, considering the material, the peculiar features of these materials, of these timbers, to maximize the durability, wherever possible.
Exactly. I think the detailing as well generally is aiming to maximize the wood's life. You can pretty almost see it in the image there, that we're generally not exposing end grain, or where it is, we're making sure it's sloped away so the top of the spindles there's an end grain there, but it's protected by the handrail. I guess those concealed, the 3 little fins that you can see sort of bottom left there, their sloped top helps carry water away. Just examples, I suppose, of keeping the detailing to maximize that. And then sort of, I guess, the inspection maintenance regime that keeps an eye on how things are behaving. The timber protection as well, and just specifying highly durable timber material.
In terms of the sort of supply chain and lead times for ordering in that, were you able to find both, say, the information you wanted on durable tropical timbers and also easily source them in good time for the program?
I think there were challenges. I probably wasn't super close to that myself. I think the wider team had sort of anticipated this. I mean, Joel, you showed it, didn't you? Early thinking about the material procurement. I think that did go through some sort of evolution as Xylotek got involved, and we really looked at where the material could be sourced. And certainly, the lead time was it always is. It's a sort of a challenge, I suppose, to find who's got what material in what dimensions in the right place. I think part of the mix of the Angelin and the Kumaru was driven by the availability of different section sizes, sort of in stock. These trees weren't felled for the project; they were held in a timber yard and in certain section sizes, and I guess consideration of sap and what state the material's in, and making sure that we're getting that super high quality that we needed. There was quite a QA process. There was more order than needed. There's quite a lot of sort of material that was rejected through that process. But
because these materials are also like non-traditional hard. It was hard to find all of the design parameters, all of the mechanical properties, for example. So there was a lot of research that had to be done in trying to find testing and checking all that. I think for some of the screws, we actually had physical testing done with some samples to confirm the capacity of the screws that, again, Rotherblast was very interested in.
Great. Got a lot of questions, but I think for time we might have to wrap things up. But a couple of people had asked for the name of the red finish stain that was applied to the timbers. So I think we'll have to ask that question.
I think I did throw it in on one of the slides, didn't I? So it's a Crown product, and it's Protec Wood Stain and Protect. So PROTEK was the red stain product.
Thank you very much. We will endeavour to answer a lot of the questions that have been asked. I will also point out that if anybody here wants to go to the TD UK site, they can find a case study on this project. We've also written a few articles on it too, so you can find a lot more information about this project on the TD UK site.
But there's sorry to interrupt. Now, there's one question I'm particularly keen to answer because it's hard.
By all means.
It's hard to notice, but someone has. I think Martin had a good picture of one of the abutments finished with the decking on top, and from that you can see that I'm just going to use my mouse to point, but basically at the end of the structure overall, including the abutment, there are no expansion joints, and all along here there are also no expansion joints. There is something that relates obviously to, this is an external structure in steel, under 70 meter long, so it will undergo some thermal expansion and contraction. We explore a bunch of different options, introducing movement joints and where to place them. Obviously, with the cassetted approach of the longitudinal decking, it would have been quite a visual break in that language. Ultimately, the solution that we were to find exploits the same lateral, sort of like less than ideal performance that I touched upon earlier in terms of the substructure being quite flexible and providing only a relative lateral restraint to this superstructure. So laterally speaking, this was only restrained at the abutment and by that cross bridge in the middle, meaning that if we were to fully constrain the bridge from a thermal movement point of view, we could exploit that S-shape curve in plan to let it basically bow out or straighten according to thermal expansion and contraction, and ultimately end up having to design for the rising forces at the abutment. That is part of the reason why we ended up designing lateral competent structures at the abutment. So basically to take that thermal force that is locked into the system, but thanks to the curve shaping plan, is not as high as it would be if it was a straight line. That's quite a unique feature hidden in the structural design of this structure.
Thank you. That's a great answer. Okay, well, I'm just going to very briefly just introduce our next webinar. Hopefully you can all see that. You can join us next month for a presentation on Whitby Walk, very different project, social and affordable housing in East London. Again, I would just say thank you to our great presenters this afternoon, and wish you all a very good afternoon. Goodbye.
Thanks, everyone.
Thank you. Bye.